This paper presents Persian classical music instrument recognition system using a novel Persian music database. The aim of the work is classification of Persian musical instruments. Features we use are mean frequency, capstone coefficients, spectral rule-off, spectral centroid, zero crossing rate, and energy entropy. For feature selection, we use fuzzy entropy feature selection method. Our classes are 7 Persian musical instrument classes, which are ney, tar, santur, kamanche, tumpak, oud, and setar. For validation, we made a small database of musical instruments, Persian musical instruments. And for classification, we use multi-layer neural network classifier. To comparison, we used a paper called Music Instrument Recognition Using Deep Convolutional Neural Networks by Solanki and partners. This figure presents the first lines of Samani, a music piece by Abul Hassan Sabah, which can be played by all melodic Persian classic instruments. This figure presents the commonly used Persian classical instruments from top left to right: ney, tar, setar, kamanche, and bottom row from left to right: santur, tumpak, and oud. This table and the following table represents the related research on the subject, which the columns are author, features, classes, classification method, year of research, and comment about the research. ESITS and partners in 2004 made a system for classification of 10 classical instruments. They used features of NFCC, spectral width, and spectral asymmetry. And they use 10 classes on a new database which they represent. And they use Gaussian mixer model as a classifier and a new pairwise feature selection algorithm based on inertia ratio maximization. They achieve 79% classification accuracy. Benetos and partners performed their method on MIS database in 2006. They use non-negative matrix factorization classification algorithm on 6 classical instruments. They use features such as spectrum flatness, spectrum flatness mean, ideal spectrum flatness variance, mean of the ideal spectrum envelope, and mean of the ideal spectrum spread, and also NFCCs. Yoder and partners used amplitude modulation, zero crossing rate, and NFCC as features on 8 classical instruments. In 2009, they used Gaussian mixer model, hidden Markov model, and support vector machine as classifier. They use spectral shape features in feature extraction method and achieved 84% of classification accuracy on ESITS database. Barbedo and the partners use combined different audio signal features in a special domain, and they worked on 25 different classical music and also voice. 2010 on RWC and Iowa database. They use SVM classifier and achieved 84% classification accuracy. Park and partners use deep learning method called convolutional neural network, or CNN, on 6 classical instruments. In 2015 on Iowa database, Iowa MIS database, and achieved 93% classification accuracy. Also, bulk used fractional Fourier transform based mean frequency capstone coefficient features on 90 different classic instruments, and they use counter propagation neural network, or CPNN classifier in 2016 on MOOM's database and achieved 95% classification accuracy. Shakib Hamidan and partners used fast ICA and MFCC as features on a small Persian music database with 6 classes. They used SVM classifier as a classification algorithm in 2016 and achieved 83% classification accuracy. Hen and partners used CNN, deep learning method, on 11 class of instruments in 2017 on IRMAS database and achieved 89% classification accuracy. Also, Solanki and partners use the same technique on same classes, and they achieved IRMAS database on the IRMAS database with 92% classification accuracy. Just they use better pre-processing techniques, and they achieved 2% more classification accuracy. This figure presents our proposed method structure. It starts from top left, loading the database, ideal signal normalization, extracting MFCC spectral centroid, spectral rule of zero crossing rate, energy entropy features, joining all features as a vector for each sample, joining all features vectors in a row, creating feature matrix for all samples, feature selection using fuzzy entropy method, labeling the features matrix for instruments, and finally classification using a multilayer neural network classifier. Now a short description on the features we used, which one of them is zero crossing rate. Zero crossing rate is the rate of sign change in audio frame, the number of signal change value from positive to negative and counterwise, divided by frame length. Second feature is energy entropy. The short-term entropy of energy can be expounded as the measure of sudden change in the energy level of digital audio signal waveform. Third feature, spectral centroid. The spectral centroid is simple measure of a spectral position and shape. The spectral centroid is the spectrum's center of gravity. Fourth feature, a spectral rule-off. Spectral rule-off represents the frequency below which a certain percentage, usually 80% to 90%, of magnitude distribution of the spectrum, which is concentrated in the spectrum itself. And final feature from frequency domain is Mel frequency Kepler coefficient. A Kepler is the result of taking the inverse Fourier transform of a logarithm from the estimated spectrum of a signal or a waveform. Now, Mel frequency Kepler or MFC is a representation of short-term power spectrum of a sound. Mel frequency Kepler coefficient are coefficients that collectively make up the MFC. Normally, first 30 MFCCs are used because they are considered to carry enough distinguishing information. MFCC commonly derived as follows. The steps are as follows. Take the Fourier transform of a signal, map the powers of the spectrum obtained above onto the Mel scale using triangular overlapping windows. Take the log of the power at each of Mel frequency. Take the discrete cosine transform of the list of Mel log powers as if it were a signal. The MFCCs are the amplitude of the resulting spectrum in short. This figure presents binary classification task of a speech versus music with MFCCs. As we can see, vertical axis shows time and horizontal axis shows the amplitude of the signal, and we can see that a speech and music could be classified very good using MFCC feature. This figure represents spectral rule-off, spectral centroid, energy entropy and zero crossing rate features in a waveform on a 2.5 seconds melody of Ney instruments. The melody waveform shown at top and at the bottom left box and right box shows its relative features in a waveform. For feature selection, we use Lucas fuzzy feature selection method. By eliminating fewer desirable attributes from the data, it could make the model clearer and more realizable. Lucas fuzzy feature selection method is used here. He used fuzzy entropy measure to remove features from data which it considered bearing least amount of relevant information. This method is based on combination of non-probabilistic fuzzy entropy and weighted fuzzy entropy. This figure shows the spectrum of each instrument in a specific duration. Each color represents an instrument, as vertical axis shows the normalized frequency and horizontal axis shows the power spectrum. For validation, we propose a small database with 7 main Persian musical instruments of ney, tar, santur, kamanche, tompak, oud, and setar. Classes consist of 89 to 110 samples. Each samples is between 5 to 10 seconds. Database is developed with the aid of musician whom he has to play and we record. Some of the pieces were played in natural places such as rooms and music shops, and a few in the music studios. This table presents the structure of our proposed database, which columns from left to right: the name of the instruments, number of samples, duration in seconds, size in megabytes, recording place, and recording device, as we have 7 different classes. For classification, we use neural networks. A neural network with enough neurons can classify almost any data. They are suitable for complex decision boundaries problems. Having many variables, feed-forward networks mostly consist of one or more hidden layer sigmoid neurons, which containing an output layer of linear neurons. In this figure, we can see the structure of a simple neural network. The left figure shows a typical multi-layer network architecture using log sigmoid transition function, and right figure shows a single layer network of S neurons having R inputs. This table presents the accurate results and comparison with reference number 35, which is Solanki method. Columns from left to right are number of hidden layer neurons, training classification accuracy, proposed method versus Solanki method, and testing classification accuracy, proposed method with Solanki method. As we can see, in training stage, as number of hidden layer neurons increases, classification accuracy increases too, but in training stage, Solanki method has privilege on our method, but in testing stage, the proposed method has privilege on Solanki method. For representing the results in a better form, we use confusion matrix. A confusion matrix is a unique table which shows the performance visualization of an algorithm or method. Usually works for supervised learning. Rows represent instance in a predicated class. Column shows the instance or samples in an actual class. Purple column indicate number of samples per class. Orange column are the percentage of misclassification and number of misclassified samples per class. Green columns are percentage of classification and number of classified samples per class. As we can see, red diagonal line shows the percentage of classification for each instrument separately, as we have 7 different instruments. We can see that the oud instrument or 7th class has the lowest classification accuracy, and tompak or 5th class has the highest classification accuracy with 95%. It has to mention that the data is split to 70% for training and 30% for testing. As we can see from left to right, green column shows the first line of green column shows the number of correctly classified samples for first class, which is ney, and also the second green column true positive rate shows the percentage of correctly classified samples for ney class. Also the orange column shows the number of misclassified samples for an A class in the first row and percentage of misclassification for the first class in the first row. Purple column shows the total number of samples for the A class. Also other rows shows the number of correctly classified, percentage of correctly classified, number of misclassified, percentage of misclassification, and total number of samples per class in each row. Finally, we have 698 samples for all classes. This figure shows the graphical form of our method on our database. As we can see, the oud instrument has the lowest accuracy and tombak instrument has the highest accuracy. From the classification results, we can conclude that in some instruments, 35 method or Solanki method has better result in training stage. In testing stage, proposed method is much better, especially when number of hidden layers increases. The highest accuracy belongs to tombak, which is a percussion instrument, and the lowest for oud, as tar, setar, and santur somehow similar. And finally, in testing stage, we get 82.57% classification accuracy. In conclusion section, we can say combination of spatial and frequency domain features are used in this research using proper preprocessing techniques, nice feature selection method, strong classifier, and the novel Persian music instrument database. Future works are increasing Persian classical music instruments like robab, qanun, daf, and qeychak, and also using a deep learning technique like CNN for classification in order to increasing the classification accuracy. In following slides, we can see the references which we use for this research. Thank you so much.